1.6.3. Radiation. You can feel the heat transfer from the sun. The space between Earth and the sun is largely empty, so the sun warms us without any possibility of heat transfer by convection or conduction. Similarly, you can sometimes tell that the oven is hot without touching its door or looking inside. It may just warm you as you walk by. In these examples, heat is transferred by radiation, figure 1.28. That is, the hot body emits electromagnetic waves that are absorbed by the skin. No medium is required for electromagnetic waves to propagate. Different names are used for electromagnetic waves of different wavelengths: radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. Figure 1.28. Most of the heat transfer from this fire to the observers occurs through infrared radiation. The visible light, although dramatic, transfers relatively little thermal energy. Convection transfers energy away from the observers as hot air rises, while conduction is negligibly slow here. Skin is very sensitive to infrared radiation, so you can sense the presence of a fire without looking at it directly. Credit: Daniel O'Neill. The energy of electromagnetic radiation varies over a wide range, depending on the wavelength. A shorter wavelength, or higher frequency, corresponds to a higher energy. Because more heat is radiated at higher temperatures produce more intensity at every wavelength, but especially at shorter wavelengths. In visible light, wavelength determines color. Red has the longest wavelength and violet the shortest, so a temperature change is accompanied by a color change. For example, an electric heating element on a stove glows from red to orange, while the higher temperature steel in a blast furnace glows from yellow to white. Infrared radiation is the predominant form radiated by objects cooler than the electric element in the steel. The radiated energy as a function of wavelength depends on its intensity, which is represented in figure 1.29 by the height of the distribution. Electromagnetic waves explains more about the electromagnetic spectrum, and photons and matter waves. http://cnx.org/content/m58757/latest/closing parenthesis discusses why the decrease in wavelength corresponds to an increase in energy. Figure 1.29. IR. Lambda, Nm. M radiation intensity. UV. Visible range, violet, red. 6000 K. White hot. 4000 K. 3000 K. Red hot. Figure 1.29. A graph of the spectrum of electromagnetic waves emitted from an ideal radiator at 3 different temperatures. The intensity or rate of radiation emission increases dramatically with temperature, and the spectrum shifts down in wavelength toward the visible and ultraviolet parts of the spectrum. The shaded portion denotes the visible part of the spectrum. It is apparent that the shift toward the ultraviolet with temperature makes the visible appearance shift from red to white to blue as temperature increases. B. Note the variations in color corresponding to variations in flame temperature. The rate of heat transfer by radiation also depends on the object's color. Black is the most effective, and white is the least effective. On a clear summer day, black asphalt in a parking lot is hotter than adjacent gray sidewalk, because black absorbs better than gray, figure 1.30. The reverse is also true, black radiates better than gray. Thus, on a clear summer night, the asphalt is colder than the gray sidewalk, because black radiates the energy more rapidly than gray. A perfectly black object would be an ideal radiator and an ideal absorber, as it would capture all the radiation that falls on it. In contrast, a perfectly white object or a perfect mirror would reflect all radiation, and a perfectly transparent object would transmit it all, figure 1.31. Such objects would not emit any radiation. Mathematically, the color is represented by the emissivity E. A blackbody radiator would have an E equals 1, whereas a perfect reflector or transmitter would have E equals 0. For real examples, tungsten light bulb filaments have an E of about 0.5, and carbon black, a material used in printer toner, has an emissivity of about 0.95. Figure 1.30. The darker pavement is hotter than the lighter pavement. Much more of the ice on the right has melted, although both have been in the sunlight for the same time. The thermal conductivities of the pavements are the same. Figure 1.31. Absorb. Incident radiant energy. Reflected. Absorbed. Black. Radiate. Emitted. Retained. Black. Absorb. Incident radiant energy. Reflected. Absorbed. Silver-coated. Radiate. Emitted. Retained. Silver-coated. Figure 1.31. A black object is a good absorber and a good radiator, whereas a white, clear, or silver object is a poor absorber and a poor radiator. To see that, consider a silver object and a black object that can exchange heat by radiation and are in thermal equilibrium. We know from experience that they will stay in equilibrium. The result of a principle that will be discussed at length in second law of thermodynamics. For the black object's temperature to stay constant, it must emit as much radiation as it absorbs, so it must be as good at radiating as absorbing. Similar considerations show that the silver object must radiate as little as it absorbs. Thus, one property, emissivity, controls both radiation and absorption. Finally, the radiated heat is proportional to the object's surface area, since every part of the surface radiates. If you knock apart the coals of a fire, the radiation increases noticeably due to an increase in radiating surface area. The rate of heat transfer by emitted radiation is described by the Stefan-Boltzmann law of radiation. P equals sigma A E T to the power of 4. Where sigma equals 5.67 multiplied by 10 to the power of negative 8 joules over second, meter squared, K to the power of 4, is the Stefan-Boltzmann constant, a combination of fundamental constants of nature. A is the surface area of the object, and T is its temperature in kelvins. The proportionality to the fourth power of the absolute temperature is a remarkably strong temperature dependence. It allows the detection of even small temperature variations. Images called thermographs can be used medically to detect regions of abnormally high temperature in the body, perhaps indicative of disease. Similar techniques can be used to detect heat leaks in homes. Figure 1.32, optimize performance of blast furnaces, improve comfort levels in work environments, and even remotely map Earth's temperature profile. Figure 1.32. A thermograph of part of a building shows temperature variations, indicating where heat transfer to the outside is most severe. Windows are a major region of heat transfer to the outside of homes. Credit: U.S. Army. The Stefan-Boltzmann equation needs only slight refinement to deal with a simple case of an object's absorption of radiation from its surroundings. Assuming that an object with a temperature T1 is surrounded by an environment with uniform temperature T2, the net rate of heat transfer by radiation is P net equals sigma Ea, open parenthesis, T2 to the power of 4, minus T1 to the power of 4, closed parenthesis. 1.10. Where E is the emissivity of the object alone. In other words, it does not matter whether the surroundings are white, gray, or black. The balance of radiation into and out of the object depends on how well it emits and absorbs radiation. When T2 is greater than T1, the quantity P net is positive, that is, the net heat transfer is from hot to cold. Before doing an example, we have a complication to discuss: different emissivities at different wavelengths. If the fraction of incident radiation an object reflects is the same at all visible wavelengths, the object is gray. If the fraction depends on the wavelength, the object has some other color. For instance, a red or reddish object reflects red light more strongly than other visible wavelengths. Because it absorbs less red, it radiates less red when hot. Differential reflection and absorption of wavelengths outside the visible range have no effect on what we see, but they may have physically important effects. Skin is a very good absorber and emitter of infrared radiation, having an emissivity of 0.97 in the infrared spectrum. Thus, in spite of the obvious variations in skin color, we are all nearly black in the infrared. This high infrared emissivity is why we can so easily feel radiation on our skin. It is also the basis for the effectiveness of night vision scopes used by law enforcement and the military to detect human beings. Example 1.13. Calculating the net heat transfer of a person. What is the rate of heat transfer by radiation of an unclothed person standing in a dark room whose ambient temperature is 22.0 degrees Celsius? The person has a normal skin temperature of 33.0 degrees Celsius and a surface area of 1.50 meters squared. The emissivity of skin is 0.97 in the infrared, the part of the spectrum where the radiation takes place. Strategy. We can solve this by using the equation for the rate of radiative heat transfer. Solution. Insert the temperature values T2 equals 295 K and T1 equals 306 K, so that Q over T equals sigma E A open parenthesis T2 to the power of 4 minus T1 to the power of 4 closed parenthesis equals open parenthesis 5.67 multiplied by 10 to the power of negative 8 joules over second dot meter squared dot K to the power of 4 closed parenthesis multiplied by open parenthesis 0.97, closed parenthesis, multiplied by, open parenthesis, 1.50 meters squared, closed parenthesis, multiplied by, open parenthesis, 295 K, closed parenthesis, all to the power of 4, minus, open parenthesis, 306 K, closed parenthesis, all to the power of 4, closed bracket, equals negative 99 joules per second, equals negative 99 watt. Significance. This value is a significant rate of heat transfer to the environment. Note the minus sign, considering that a person at rest may produce energy at the rate of 125 watt and that conduction and convection are also transferring energy to the environment. Indeed, we would probably expect this person to feel cold. Clothing significantly reduces heat transfer to the environment by all mechanisms, because clothing slows down both conduction and convection, and has a lower emissivity, especially if it is light-colored, than skin. The average temperature of Earth is the subject of much current discussion. Earth is in radiative contact with both the sun and dark space, so we cannot use the equation for an environment at a uniform temperature. Earth receives almost all its energy from radiation of the sun and reflects some of it back into outer space. Conversely, dark space is very cold, about 3 K, so that Earth radiates energy into the dark sky. The rate of heat transfer from soil and grasses can be so rapid that frost may occur on clear summer evenings, even in warm latitudes. The average temperature of Earth is determined by its energy balance. To a first approximation, it is the temperature at which Earth radiates heat to space as fast as it receives energy from the sun. An important parameter in calculating the temperature of Earth is its emissivity, E. On average, it is about 0.65. But calculation of this value is complicated by the great day-to-day variation in the highly reflective cloud coverage. Because clouds have lower emissivity than either oceans or land masses, they reflect some of the radiation back to the surface, greatly reducing heat transfer into dark space, just as they greatly reduce heat transfer into the atmosphere during the day. There is negative feedback, in which a change produces an effect that opposes that change between clouds and heat transfer. Higher temperatures evaporate more water to form more clouds, which reflect more radiation back into space, reducing the temperature. The often mentioned greenhouse effect is directly related to the variation of Earth's emissivity with wavelength, figure 1.33. The greenhouse effect is a natural phenomenon responsible for providing temperatures suitable for life on Earth and for making Venus unsuitable for human life. Most of the infrared radiation emitted from Earth is absorbed by carbon dioxide, CO2, and water, H2O, in the atmosphere and then re-radiated into outer space or back to Earth. Re-radiation back to Earth maintains its surface temperature about 40 degrees Celsius higher than it would be if there were no atmosphere. The glass walls and roof of a greenhouse increase the temperature inside by blocking convective heat losses, not radiative losses. Figure 1.33. Atmosphere. UV. Visible. IR. IR. Figure 1.33. The greenhouse effect is the name given to the increase of Earth's temperature due to absorption of radiation in the atmosphere. The atmosphere is transparent to incoming visible radiation and most of the sun's infrared. The Earth absorbs that energy and re-emits it. Since Earth's temperature is much lower than the sun's, it re-emits the energy at much longer wavelengths in the infrared. The atmosphere absorbs much of that infrared radiation and radiates about half of the energy back down, keeping Earth warmer than it would otherwise be. The amount of trapping depends on concentrations of trace gases such as carbon dioxide, and an increase in the concentration of these gases increases Earth's surface temperature. The greenhouse effect is central to the discussion of global warming due to emission of carbon dioxide and methane, and other greenhouse gases, into Earth's atmosphere from industry, transportation, and farming. Changes in global climate could lead to more intense storms, precipitation changes affecting agriculture, reduction in rainforest biodiversity, and rising sea levels. You can explore a simulation of the greenhouse effect. https://openstaxcollege.org/l/21simgreenif that takes the point of view that the atmosphere scatters, redirects, infrared radiation rather than absorbing it and re-radiating it. You may want to run the simulation first with no greenhouse gases in the atmosphere and then look at how adding greenhouse gases affects the infrared radiation from the Earth and the Earth's temperature. A. Problem-solving strategy. Effects of heat transfer. 1. Examine the situation to determine what type of heat transfer is involved. 2. Identify the types of heat transfer: conduction, convection, or radiation. 3. Identify exactly what needs to be determined in the problem. Identify the unknowns. A written list is useful. 4. Make a list of what is given or what can be inferred from the problem as stated. Identify the knowns. 5. Solve the appropriate equation for the quantity to be determined, the unknown. 6. For conduction, use the equation P equals Ka delta T over D. Table 1.5 lists thermal conductivities. For convection, determine the amount of matter moved in the equation Q equals m c delta T, along with Q equals m Lf, or Q equals m Lv if a substance changes phase. For radiation, the equation P net equals sigma E A, open parenthesis, T2 to the power of 4 minus T1 to the power of 4, closed parenthesis, gives the net heat transfer rate. 7. Substitute the knowns along with their units into the appropriate equation and obtain numerical solutions complete with units. 8. Check the answer to see if it is reasonable. Does it make sense? 1.9. Check your understanding. How much greater is the rate of heat radiation when a body is at the temperature 40 degrees Celsius than when it is at the temperature 20 degrees Celsius?